Let's now talk about the system property of Deadlock Freedom. It's actually a very simple one to actually introduce and also to formulate. Yet it's a very useful property that your system may actually just want to have and to be proved having that particular property. So that's something we'll like to do quickly, and then we can do some proofs together. Right, let me remind you very quickly that so far we actually talk about how we can establish and also preserve the invariance conditions in our model, and we can use that as a very useful feedback to see if there's any revision that's necessary for our model. That's something we have done so far, right? I'm just gonna list the bullet points over here, but you want to make sure you really understand the distinction between having to establish versus having to preserve the invariance. That's something I'll leave to you. And let's talk about Deadlock Freedom, which really has to do with the guards of the events. So if you just try to recall, in the very beginning of our initial model, our first version of the initial model simply got ML out and ML in, simply unconditional, meaning that we simply don't really have any guards. And I said to you before, if you simply don't have the guard for a particular events, that means it will be as if you actually got true for the guard of the events, meaning that the event is always enabled, so you can always invoke the events. What event will always just occur without having to be blocked or having to be disabled. However, as soon as you introduce some guards into your events, in that case, there is a possibility that you might just run into deadlock. So that's something you definitely want to make sure. On the one hand, you know that having the events totally unconditional without any guards is actually not a good sign, right? As we said before, because you might simply just violate the invariance at some point. But on the other hand, whenever or as soon as you introduce guards into your events, there is a possibility, unless you can actually formally prove it is not the case, that maybe there will be one particular system states where all the guards for all the events will simply evaluate to false, in which case all the events will be disabled, in which case there's no way for your system to really make any concrete progress, right? So these are the two things, more like a dilemma you really want to make sure understand, right? Let me say it once more. On the one hand, you definitely don't want your system to be guard free. You definitely want it to have some guards. And on the other hand, as soon as you have guards for the events, you might run into the deadlock situation where all the events are disabled because their guards evaluate to false. Right? It's a very important dilemma for you to understand. Right? So a state where the guards of all the events evaluate to false, as I said, in which case no events will be enabled. All of them will just be disabled, which means there's simply no occurrence of anything in your system. Your system simply stays silent. It's simply deadlocked, right? That's what we said. So that means your system is blocked and it's not reactive anymore, which will be very ironic for a reactive system, right? So if you really build some reactive system, you want it to be reactive to the outside world all the time. But if suddenly it simply stopped to really react to any outside stimuli, in that case, you definitely would not want such property to be violated. So you definitely want your system to be deadlock free. So we're going to express this non-blocking property as a new requirements. So you can see we are using two terms interchangeably. Either you can say your system deadlock, or you can say your system is actually blocked, right? Or you can say you want your system to be deadlock free. That's a property. Or you can simply say you want your system to be non-blocking, right? So these are the synonyms you can use interchangeably. Accordingly, we would like to introduce one more requirements for our system, for our bridge controller, which is requirement number 4. Once started, the system should work forever, which means it should never deadlock. You should never be blocked, right? That's the new requirement that we're introducing to our bridge controller system. And for many systems that you might build using the formal methods, you may just want this requirement as well, right? Just it really depends case by case. Let's now see, go a little bit further into well, we already understand the intuition about deadlock freedom and also why you don't really want your system to really deadlock. And exactly how do we actually formulate the deadlock freedom property? Let's see. So let's recall some of the formal components that we discussed earlier when we actually formulate the proof obligation for invariant preservation. We can certainly reuse them because they actually extract the useful components from our model. So we got constants, we got axioms, we got variables in both the pre and post states, and also the invariants, and also we got the guards for the events. Specifically, because the deadlock is really as a consequence of all the guards for all the events are simply not really evaluating the truth. They are simply evaluating the false, meaning that all the events are disabled. So the guards are particularly relevant in the case of the deadlock freedom, right? So I'm gonna let you review all the components if necessary, because we spoke about it in detail in the earlier part, so we don't have to repeat right now. Okay, so what we do is we want to really formulate the proof obligation for deadlock freedom as a sequence, right? Just like how we formulate a proof obligation for invariant establishment and also for invariant preservation. So now we're going to have our third proof obligation rule for deadlock freedom. But before that, let's now do some informal sketch. You can also try to imagine how it's going to look like, right? You can also help you understand about the sequence, syntax, and semantics more. So to really prove about deadlock freedom, we want to say at least one. So whenever we say at least one, what kind of a logical operator should we use when we say at least one, right? So that means it doesn't need to be all of them being true, so at least one being true. Sounds more like a disjunction idea, like an or idea. So we want to say at least one of the event guards is actually true, or at least one event is enabled. At least one. If there's at least one event that's enabled, that means we can the system can at least have that event occur and make some progress. Maybe after the occurrence of that event, other events will suddenly also become enabled, right? So you really that's kind of the idea. You want to make sure at least one event is enabled at any one time for a system not to be blocked or not to be deadlocked. Okay, that will be the informal sketch. You can see we got a new rule named DLF. You can think about deadlock and also freedom, DLF, standing for deadlock freedom. And so this is an informal sketch. So it's a turnstile, it's a sequence. What's the hypothesis? We assume two things. One is about the axiom, right? And the other thing is about the invariant being satisfied in the pre-states. And given these two assumptions, we want to prove that as a consequence, the disjunction of the guard satisfied at the pre-states. So we want to make sure at least one event actually got its guard evaluating the truth. So that's why we say disjunction. You can think about the disjunction here is really the formulation for at least one event being enabled, right? Let's now take a look at the formal rule, and then I'll do some annotation and we'll do some exercise together specific to our model M0. So that will be the rule over here. So we got the axiom over here, and also we got the invariance in the pre-states over here, and also we got the disjunction of all the guards. So here we're assuming that this might be event number 1, its guard, and also up to event number n. So we got n events. But if you only got one event, there's only one just the guard for the single event itself. If you actually got two events, event number 1, event number 2, it should be guard number 1 or guard number 2. If you actually got 3 events, it should be guard number 1 or guard number 2 or guard number 3, right? And etc. So that's why we simply use dot 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 over here to really indicate, in general, you just have to disjoint the guards for all the events together. And one thing you may just notice already, right? You can see that in the case of the deadlock freedom over here, it's kind of a very different from actually the invariant preservation, and also very different from the invariant establishment. Specifically, you can see in the hypothesis and also in the goal over here, we don't really need to refer to the post states, especially over here, right? You can see this part over here is kind of similar to what you had to assume in the case of the invariant preservation, right? But in the case of invariant establishment, there's no notion of the pre-state, just to remind you. However, this part here is actually quite different. Recall what's really in the invariant preservation rule. In the goal for the invariant preservation, we say that the invariant must be maintained in the post states. That's why we had to use the effects of the event, the capital E. But in this case, we don't have to. You can see this, there is no V prime. It's only the pre-state value over here. So that's really the nature reflection of what the is really a reflection of what the nature of the rule is, right? Let me do a little bit of annotation and then we'll do some exercise together. Okay. Right, again, we got our new requirement number 4, once started, the system should work forever. So we really try to work around this particular requirements over here. Try to formulate it and also try to prove it. And this is our initial model over here. Remember, that's the revised one. So we have already added the guards for MLL and MLN because we wanted to preserve the invariance. And so here for Deadlock Freedom, we don't really have to worry about initial events, right? Something just to notice right away. Whenever we talk about Deadlock Freedom, we are talking about once the system has already started, right? Once started, okay? So that means over here, so once started over here, so this means the initial events is not relevant in the case of Deadlock Freedom because you can always initialize your system without worrying about the pre-states. Not relevant. That's one thing we can observe right away. Simply not relevant. And then we got the 2 events over here, and they also they have their guards. And we got our constant, axiom, variables, and invariants as before. Okay, and that's the rule over here. And let me annotate right away. It's so important for you to see the variable over here for the invariance in the hypothesis, and also all the v over here, all the variables over here. So these are all the variables in the pre-states, right? This one here, and also this one here. They all refer to the pre-state values. Right? So we only worry about whether there can be a transition taken by at least one event. So in order for a transition to really be applicable, the pre-state value must satisfy its guard. So that's why we're only talking about pre-state over here. And so these are just the formal components over here. I'm simply including them over here just for your convenience. You should really review them. Specifically, we need this particular guy here. We need a guard, and also we need an invariance, and also we need the axiom. So these are the 3 things you will see in the rule. Okay. There's one more before I actually do the exercise together with you. I want to do one quick comparison over here, right? If you think about the several things that we really care, right? We care about pre-states, and also we care about the post-states. So these are the 2 states for every variables that we may actually refer to. But we don't necessarily have to refer to both of them for every proof obligation rule. So let me just do some quick summary together with you. That's not really in the slides. I thought it might just be nice when we do this comparison together. And the table over here, I'm going to say for each row, we're going to talk about different proof obligation rule. Right? So here we talk about the proof obligation. Okay? Proof obligation. So one is about invariance establishment, EST for short, and also invariance preservation. I'll just say preservation, and also for deadlock freedom, DLF, right? So these are the 3 proof obligation that we have done so far. Well, not deadlock freedom, not completely, but that's what we are doing. Now I want you to think about, in order to formulate each one of the proof obligation over here, which state is actually relevant. And for the state that's not relevant, we can just say NA, not applicable. All right. Let's first of all start with invariant establishment, in which case we only worry about the post states, right? That's all we care. In the case of the pre-state, it's not applicable. There is no notion about the pre-states for the init events. Right? That's number 1. And for number 2, what about for the invariant preservation? Invariant preservation, remember, it's more like an inductive cases for the mathematical induction. So you want to make sure you assume the invariant actually is satisfied in the pre-state as the hypothesis, and you want to prove that it's maintained in the post-states. So both of them should be relevant. All right. Finally, let's now talk about the deadlock freedom over here. For deadlock freedom, what about it? Well, for the deadlock freedom, you don't really worry about the consequence of taking the transition. You want to make sure the transition can be taken in the first place. So that's why only the pre-state will actually matter. That's the only one that's relevant. In the case of the post-state, it's simply not applicable, right? Right? I think this table is really important to really show to you the proof obligation rules that we have done so far, and to know which one of them is going to refer to the pre or the post states. Right? Especially, I want you to pay attention to this cell over here and also this cell over here. All right? Hopefully, this comparison and summary is actually useful. Let's go back to our Deadlock Freedom proof obligation rule. This is the rule, and we would like to now try to instantiate this rule using our initial model M0. Right? Again, this is our final version of the M0. Well, actually, not the final version just yet, because when we try to prove the proof obligation rule for Deadlock Freedom, we might realize maybe there's something that we gotta revise further for our model. So I'll just say it's M0. It is still the work under construction, right? How do we actually generate the sequence? First of all, how many sequence do we need in order to really to instantiate from this particular rule? Does it really depend on how many events we have? For example, if we actually got 2 events over here for ML out and ML in, do we have to generate 2 sequences for Deadlock Freedom? One for ML out and one for ML in? The answer is no, because that's really the nature of the rule. It's so important. You're trying to disjoint all the guards together from all the events. You don't really talk about individual events in isolation. So there is always only one particular sequence you have to generate to formulate the proof obligation for Deadlock Freedom. Right? Let's now do it. So what I would do is I'm going to put the turnstile over here, right? So what will be the hypothesis? The hypothesis will be over here, right? This will be hypothesis. Hypothesis will just be the axiom. So for axiom, this is what we have, right? Axiom will be D is a member of natural number. And also we got a invariance, right? All the invariant, you can see there's no particular index, just I. So the entirety of the events. So it's going to be N is a member of natural number. And let me move this a little bit down over here. And also the second one, N is less than or equal to D, right? So these are the 3 hypotheses over here, right? This part over here is the axiom. These 2 things are the invariant condition, the 2 invariant conditions. All of them should be included as a hypothesis. And how do we express this over here? Well, easy. All you got to do is you're going to take the guards for from all the events and then put them into disjunction. Let's see. So we got one guard over here for the first events. We got a second guard over here for the second event, right? So we're going to put them together. So we're going to put over here is going to be N less than D, and also N larger than 0. And it's going to be the disjunction. So we're going to put disjunction over here, right? And one more thing I would like to emphasize one more time. You can see over here, we are using N over here. And also we are using N over here. And also we are using N over here. And also we're using N over here. Right? So they all refer to the pre-state value. Okay, let me just draw a little bit better. Okay, all of them refer to the pre-state. Number 1. And number 2, the before-after predicate is simply not relevant over here. The before-after predicates of event actions is irrelevant. Okay, let me write down the reason, which I also mentioned verbally. Because we are not concerned about effects of event action. Right? Number 1. Number 2, instead, we are concerned about if there is even a transition in the first place. Yeah, sorry about writing everywhere, but hopefully it's still clear to you in the first place. Right, so both points are very important. I didn't really put it in the slide intentionally because I think it's really good to have such remarks when you got all the relevant pieces in a single page. Okay, so here let me just highlight the before-after predicate is simply irrelevant. Okay, because we are not concerned about the effects of the events. We are only concerned about whether there's even a transition in the first place, meaning that there will be at least one event whose guard is actually true, meaning there's at least one event that's enabled, right? Right, you can see the sequence generation itself is actually pretty easy, pretty straightforward, but you really want to understand exactly why we don't really have any mention of the post states. It's simply not relevant. And also refer to this table over here to make sure you also understand the comparison and contrast among all the three proof obligation rules we have spoken about: invariant establishment, invariant preservation, and deadlock freedom. Alrighty, let's now go back. And to really prove about deadlock freedom over here, you can see the state transition is simply not relevant, as I just remarked. And also, we instead, the evaluation for all the guards, whether or not the transitions can be taken in the first place, we are concerned about that in the pre-states. Okay, yeah, I think there's one more slide before we go on to the proof. Okay, so deadlock freedom, let me emphasize, is not necessarily a desired property for every system. For many systems, deadlock freedom is very important. For example, for our bridge controller, once the bridge controller is really put in function, is launched, we definitely don't want it to be deadlocked, right? We definitely want cars to be able to make progress either to the mainland or outside the mainland. So when it is actually relevant for your system, you will have to make sure the generated sequence are discharged, right? Actually, so here I say plural, it should be singular. When the generated sequence, there's only one sequence for the deadlock freedom for your system. I'm gonna fix this, okay, just to be more precise on the wording. Right, so after applying the deadlock freedom rule, which I already did, so this will be the final outcome, right, for our the deadlock freedom sequence that we need to discharge for our initial model N0, right? That's something exactly what we did over here, right? Of course, you should really understand exactly why we're only referring to the pre-states about the guards for every event over here in this junction. So our bridge controller being deadlock free means that the cars can always enter and leave the mainland, right? Between the mainland and also the island bridge compound, right? Let me just go back to the diagram about our abstraction over here. It might be nice to talk about it. So when you say this particular system is deadlock free, that means it's always possible either for a car to go from the mainland to the compound, or there's a car to go from the compound to the mainland. Either way is okay. But if you reach a particular state where it's neither possible to do this nor possible to do this, in that case your system is deadlocked, which is definitely not good. You don't want it to happen, right? Let's go back. Right, so here is a question here. Can we formally discharge this proof obligation for our initial model M0 with respect to deadlock freedom? Can we discharge this, right? That's a question, right? And before that, I would say you can definitely think about how you may sketch the proof. Are the example inference rules that we have covered so far enough for you to actually discharge this particular sequence? You can think about it, and if no, then you can watch the next video to see some hints from me.